Chat window. All right. Let's see. Can everyone hear me? Or maybe that's too much to ask. Can anyone hear me?
Yeah.
Gotcha.
Yes.
All right. As long as we're not at 0, it's okay. All right. Okay. Camera good. That's on. So any, oh wait, it's only 10:29. Early. Very efficient getting things. Oh yeah, hardly anyone's here yet. And I'm going to assume that's because it's 10:29. Let's just go with that. All right, so just give me a minute.
Where am I? Where's Reznov?
All right. The clipboard is back. Okay, let's see. Anything administrative we have to talk about before we start?
Can you move it left just a little bit, the clipboard?
Yeah.
Oh, fantastic.
All right. Well,
Doug
wait.
just mentioned something about a break, and I know that's soon, but I know that because of COVID, everything, we're not doing breaks. So what's with that? Or are you a great professor and you're giving us a break?
No, that would be a terrible professor, right?
Pretty sure we don't have class Tuesday, right? Monday.
Yeah, we follow whatever this university schedule is, but I believe it's, hang on, give me 1 second. It's in the day-by-day syllabus, which I know you have all studied closely. It is, yeah, we have class today and Thursday, and then next Tuesday, there is no class. And so if your discussion section happens to fall next Tuesday, you'll just have one fewer discussion and one
mine falls on Monday, and our TA said like we don't have class Monday either.
Oh, okay, that may be. It's all about me. I don't have class next Tuesday.
I know.
I don't know. Having 0 days off, and they were like, yeah, right, that's right. So it's yeah, there's 1 day in March. I guess there's right, 1 day in March, and so there was a day off in March.
Yes, it was Wednesday, like Wellness Wednesday or something like this.
Right. Again, since I don't teach on Wednesday, it's like, well,
I mean, I have like 0 classes on Wednesday, so nothing changed.
Right. Yeah. So it's next Tuesday, which just for just saying it was in the syllabus. It's the day-by-day syllabus list is no class. So you heard, right? There's this story of this is the story. Some professor committed a murder, but he was never caught because he wrote his confession in the syllabus.
I've actually been using the syllabus quite a lot to help me know what to study.
Yeah, I find it useful.
I found it incredibly helpful, and
And
I'm
no
very
one
glad
read
you
the
did your
syllabus,
syllabus the way
right?
you did.
Exactly.
Yeah, exactly. I'm glad to. I've been using it to keep track of like test and quiz dates and what material we have to be caught up with and all that.
All right. Excellent. Okay. Yeah, Alistair, it's not risky. Usually nobody reads the syllabus, but apparently a few people are, so that's good. Okay, so where we left off, and so the on the second chance exam, they're obviously all graded. They're out of 80. I don't know, the scale of what's A, B, C, D is probably about the same as the first exam. Honestly, I have not looked through the exam to compare it to any other exams or other people's exams. So, but I think it was a fairly similar level. So, hang on.
Professor, before we get started, I sent you an email like 2 weeks ago. I need a form filled out and it's due by Thursday. If you could
Yeah.
look at it.
Yeah, I will. I remember your email is flagged and it's in a giant pile of other flagged email. But yes, if you don't see it tomorrow, bug me and say what the hell's going on. So, okay. So where we left off, right? So this chapter it's an entire chapter about this one equation. And as we talked about it, the order of things is sort of backwards. You would expect that first you would learn how B fields are produced, and then you would learn about the force that B fields impart on charged particles. But it's not usually done that way, and your book doesn't do it that way, because calculating B fields from currents is more complicated than finding the force on charged particles from B fields. And so as a more gentle introduction, it's standard practice to do this first. And so this is known as the Lorentz force equation. Right, so it simply says if you have a B field pointing in some direction, and I have a particle of charge Q moving in this direction with Q is not a vector, but V is a vector. Some particle of charge Q moving with velocity V this way. The force on this particle is its charge times its velocity crossed with it with the B vector. So in this case, V goes this way, B goes that way. And so V cross B would be into the page. And we'll follow the standard convention of we write X's for vectors that point into the page and dots for vectors that point out of the page. So in this case, the force vector, we'd write sort of like that. And it goes into the page. And you have to be careful, of course, because if this is a negatively charged particle, right, if the force is into the page, if Q is positive, if Q is negative, V cross B still points into the page, but Q times V cross B would point out of the page because you'd multiply V cross B by a negative number. Okay. And we did some examples with that. In some cases, you might know the angle between, you know that the magnitude of the vector V cross B is equal to the magnitude of V times the magnitude of B times sine of theta, and the direction of the vector V cross B, the result of V cross B is a vector. You can get that from right-hand rule. And sometimes you may know the opening angle between V and B, which that makes it simple. Sometimes you don't. Sometimes you just know V and B in terms of how much, V sub X, X hat, plus V sub Y, Y hat, plus V sub Z, Z hat, crossed with this vector. You may also know in components, it has some amount of X component, plus some amount of Y component, plus some amount of Z component. And you'd have to cross these out using, what you know of X hat cross Y hat and Z hat cross X hat and 9 terms, 3 of which will be 0, 6 of which will be non-zero. And you can do that little matrix determinant trick to get to that quickly if you like that way of doing it. So we did some examples with that. And let's see, let's actually skip that for now. So questions so far? Which symbol is in? No labels. This one, this is I was pointing out here, Eric, that in general, in this chapter and ones that come up, we're going to have a lot of things in three different directions. And it's standard practice to write X for a vector that's going into the page and dot for a vector that's coming out of the page at you. And so it just basically, it's sort of like meant to be the fins on the back of an arrow or the point of an arrow if it's coming toward you or away from you. Okay. Oh, Evan, yeah, it's not that there are discussions next week. Only if your discussion is on a day in which their classes are canceled is your discussion canceled. So people on, if they're, I guess it's Monday, Tuesday. I thought it was just Tuesday. But in any case, if there are no classes on a particular day, those discussions are canceled. All the others are in place. And in fact, if you want to go, you can have the best of both worlds if you feel like it. If you want to go to another discussion section and just sit in so that you have a chance to ask questions because your discussion is canceled, zoom into a different discussion section. And if you don't want to take the quiz, don't take the quiz because your discussion section doesn't have a quiz that week. But you can still go, and then you can ask your questions and see more review of material if you want. Okay. So, and that's true in general. You can always, in any week, if you go to your discussion section, but you want more time to ask questions, go to another section and sit in on as many as you like. It's one of the few upsides of Zoom, but it is an upside. There's no space limitations in classes. If you're in Monday's discussion, he said we have, all right, well, all right. Malay, I don't know what that's about. I'll talk to Nick. Okay. So let's take a look at a case where you have a particle. Let's keep the charge positive. Oh yeah, I'm sorry. If the syllabus says there's no quiz next week, then nobody has a quiz next week. Yeah, exactly. Who's not checking their own syllabus? It's a valid point, Asa. How do I mute you?
Professor, I have just one quick question before you move on. So for in the above half of like the page, is V the vector of the charge or like the velocity, or is it the same thing?
Yeah, that's why I was just a little sloppy in writing it. So it is a particle of charge Q that is sitting at this spot, and its velocity vector is this.
Okay, velocity vector. Thank you.
Right, so Q times velocity cross B field. So let's suppose we have a particle of charge Q, and its velocity vector is this way. So it's here, but its velocity vector points that way. And let's say there's a B field into the page. So again, using this convention, X's are vectors pointing away from us. So the B field is into the page. So the question is, what direction does this thing move? Right, so let's say the B field extends way. So this thing is in the middle of some giant region of B field that's into the page. Well, take a second on your own and figure out the direction of the force on this charged particle. It's plus Q moving in that direction and a B field into the page. So do this to get the direction right. Right, so take a minute and do that. And you can just put it in the in chat, but don't look at the chat window if you're still figuring it out on your own. In fact, actually, let's we should do a poll if I can figure out how to do it. Yeah, here we go. All right, so the direction of the force on this particle at this instant. Up, down, left, right, in, or out. One trick to remember with cross products is the result of the cross product has to be perpendicular to both of the vectors that went into the cross product. So the V cross B is perpendicular to V and it's perpendicular to B. V goes that way, B is into the page. There are only two directions that are perpendicular both to V and to B. And so all you're using the right-hand rule for is to choose between the options. Right? V is this way, B is that way. So the only directions perpendicular to both V and B are this and that. Up and down are the only possible options. And you're only using the right-hand rule to choose between them. So V is this way, B is into the page, V cross B is this way. So the force at this moment, the force, again, most people have that. Okay, good. So the force at this moment is this way. Okay, so fine. So that means its velocity vector is that way, but the force on it is that way, which means it's going to shift a little bit this direction. And so now its velocity, it moves this way, but a split second later, now its velocity vector is like that. And when it's here, remember the V cross B, if you're crossing V with B into the page, the only directions possible are that one and that one. And you're using the right-hand rule to check between them. And so it's that way. It's the force. And then it's going to move a little bit more this way. And so you get the idea what's going to happen. And this is obviously not a formal proof of it, but the particle is going to move in a circle. Right? So at any point, its velocity vectors are like this, and the force vectors on it are always perpendicular. So the force, when it's here, the force vector is down. When it's here, the force vector on it is this way. Right? So the velocity vector and the force vector are perpendicular. And in fact, so it's not, we're not formally proving it moves in a circle, but whenever you have a case where the force on an object is always perpendicular to its velocity, that is circular motion, right? And it's one of my personal gripes is, right, people get confused about this, like why is it perpendicular if the force is perpendicular? So if the acceleration is perpendicular to the motion, why does that force it to move in a circle? And I think the reason people have trouble seeing that is some people incorrectly think of vectors as having positions. They don't. And so at this instant of time, if something is here, its velocity vector is like that. And then a little bit later, it's here. And its velocity vector is now like this. And so then when you think, well, how does V change? In other words, what's the acceleration, right? You know, something moving in a circle is accelerating toward the center. But it kind of never seems that way, that something moving in a circle doesn't seem like it should be accelerating toward the center. It tends to be something people remember but don't quite see. And that's because when you think of some people, when they think of this, think, all right, the velocity vector was there. Now a split second later, the particle's here and the velocity vector is like that. That change in velocity vector from here to here, which is what acceleration is, the change in velocity, sure doesn't look like it's aimed at the center. It's kind of aimed this way. And you only think that if you leave this vector here. What you really want to be thinking of is that if you were to track the velocity vector as this thing moves around in a circle, initially when it's at the top, the velocity vector looks like this. A split second later, the velocity vector, which has no position, has changed and it's now like that. And a little bit later, it's now like this. And a little later, it's now like that. And so if you ask, what is the difference in velocity vector from when it's this to a split second later when it is just turned a little bit? The speed is the same, and so its length is the same. So a split second later, it's just this vector has turned by a tiny bit, and that change is directly pointed to the center. Right? So if you have a vector that starts like this and it's changing and going around like this change is always toward the center, right? Perpendicular to its motion, and that gives you